Hi, welcome back to Cracking the Cryptic, where I hope some of you who might be interested in such things have seen that, oh, it's all going kicking off on the screen there. I've seen this article by Alex Bellos, the famous puzzle author that appeared in The Guardian yesterday here in the UK, about Sandwich Sudoku, as he calls it, which is between 1 and 9 Sudoku, as we've been calling it on the channel. And he discusses one of our videos in this article. You can get it online. I'll put a link in the chat, but it's nice to get a bit of media coverage, so we're certainly very grateful for that. And I think it shows we're on the right lines regarding what we're doing with the channel in general. But today I'm not doing a between 1 and 9 Sudoku or a sandwich Sudoku. I'm going to do this puzzle, which Matthias has sent in from Denmark. Two reasons I'm going to look at it. Firstly, he's from Denmark, so it helps us with our quest to go round the world with extreme Sudoku puzzles. Secondly, this is an extreme Sudoku puzzle, so each week I try and do one puzzle which is monstrous. He assures me this is monstrous, so I don't know why it's monstrous, don't know what techniques are involved, but I think we should be in for a challenge. Some of these videos get a little bit long, so apologies if that's the case here. I'm using Duncan's Sudoku Solver, the new edition now, thanks to those of you who pointed me in this direction. I love it because, look, I can just switch between big numbers and little numbers like this. So without further ado, let's take a look. And in fact, 1, 6 and 2 in this top row here, look at that. Where do I put the numbers 1, 6 and 2 in this block? Well, I can only put them in those positions. So let's start there. Just checking, see whether or not I can do any more eliminations. I'm not seeing anything. So 3, 4 and 7 now up the top here, which means this must be 8 or 9. So we identify a pair in this grid. Oh, it's 3 by 3 blocks straight off the bat, and then look, there's a 5 and an 8 here and a 5 and an 8 here. So 5s and 8s can only go in 2 positions in this block. I thought one of these things would give me a digit, but no, neither of them seem to have done. I can get a digit another way. 7s and 7 here. And in fact, these two 7s give 2 digits in the grid, because they give a 7 in this block and in this block. That's quite nice, isn't it? 7 goes here, and 7 must also go here. So let's switch to some Snyder notation. So Snyder notation is just notating in 3 by 3 blocks if a number can go in exactly 2 positions. So you can see we can trawl around. This 4 here, that locks a 4 into this square. We trawl around the grid and see what we can see doing this. There's nothing clever about this. In many ways, it's just how quickly can you do it. Certainly, if you're in a speed solving context. Where can a 5 go in this middle block? Only here. So we put that in. This 5, this 5, and this 5. And we need 1, 6 and 9 to complete this 3 by 3 block. So let's put that in, 1, 6 and 9. And that resolves the 8-9 pair we found at the start. And that resolves the 8 pencil marks I just put in. So we're off and running here. 9s. 9, one of these 9s from down here, and the 9s in these 2 positions means this is a 9. And that means this is a 4. All I've done there is unwind the earlier pencil marks. What I said was I was going to notate numbers in exactly 2 positions in blocks. So once this 9 absorbs one of those positions, the other number must be true. So once the 9 was placed where I pencil marked a 4 in this block, this pencil mark must be the true 4. You can see that's going to give me a 4 here. Again, 4, 4, and this 4 here interacting, and that allows me to do that as well. And what can we do now? We've got quite a lot of densely filled columns here, so let's have a look at this one. We need 2 and 3. Bother. But I'm very tempted to pencil mark that in, I have to say, because that's such a powerful restriction. So just, oh, in fact, what am I doing? There's a 2 here. Am I just going mad? Apparently so. So, yeah, let's do it like that. That means we've got a 1 and a 6 into these 2 squares. This can no longer be a 2. And 6, 7 up here. See, no 6s and 7s in rows 2 and 3 yet, so I can't really restrict that further. 6, 7. And then up the central column we need 1, 3 and 6. And again, I've got no 3s on either side there to help me out with that. Don't forget this 5, 8 pair. Okay. But I feel we've made reasonable progress. Just hope I've not missed anything else easy. So let's look at this row now. 1, 3 and 6 again. Again, nothing. 1, 3 and 6 into these 2 squares. And I think now it feels like in a moment at least I'm going to have to abandon these pencil marks, the Snyder notation, because I want to go towards a more comprehensive form of notation generally in order to try and identify those squares that are particularly restricted. So let's take a quick look at column 1. 1, 3, 7 and 8. 1, 3, 7, oops, 1, 3, 7 here, 1, 7 here. See anything with that? 1, 8 here, and 1, 3, 7 or 8 here. So now here is something. Look, we have a 5, 8 and a 9 in this block. Now this is a trick that I practice a lot because I do the New York Times hard Sudoku every day. And if you do the New York Times hard Sudoku every day, you will get very good at spotting hidden triples because it does this all the time. Now in this instance actually I couldn't have done this from the very first moment that we opened the puzzle because I wouldn't have had enough pencil marks to see the hidden triple. But look, where can we place a 5, 8 and a 9 in column 3? Can't put one in any of these 3 squares. And that means there's only 5 positions open for these 3 numbers, i.e. this one, this one, this one, this one, and this one. But look, 9, 8, 5 is already there in row 5, and 9, 5, 8 is already there in row 6. So there's only 3 positions that the numbers 5, 8 and 9 can go into. That's one of them, that's one of them, and that's one of them. So we get a 5, 8, 9 triple in the column. Now, does that matter? We may ask ourselves. Surely it matters, but why? Don't know. But there's 2's here, look. So that I could have got from the start as being a 2. Now there's only, well, I'm not sure if it's now there's only 1 position that a 2 can go to in column 3. I'm not sure whether the 5, 8 and 9 helped us with that or not. Yeah, it did, because it ruled out 2's from both of these squares. So actually, that was helpful. We've backed into a 2 here, which unfortunately isn't going to be much more helpful than that, because the 2's here and here are pretty open. 5, 8, 9, 1, 6, 7 into this square. Okay, and there you go. Now there's a bent triple going around the corner here. 1, 6 and 7. So this is not quite a Y-wing. A y-wing would be if this square couldn't be a 1. So if this could be only a 6 or a 7, this 1, 6, 7 bent triple here would be a y-wing, and we would know that there would have to be a 1 in one of these two positions. Now, the interesting thing about adding the 1 in here is that it's still powerful enough to give us a restriction, because I suppose the best way of asking ourselves the question is, you can see that 1 is common to all of these three cells in this triple going around the corner here. Now, is it possible that none of these squares contains a 1? So if we looked at the finished solution, is it possible that that exists as a solution? Clearly it's not, because if there's a 7 here and a 6 here, this square here now can't be filled. So the corollary of that is that there must be a 1 in one of these three positions, possibly two of them. But therefore any cell that can see all three of these cells can never contain a 1, because we've just proved there must be a 1 in at least one of them. So this square can't contain a 1. So it sees this one, it sees this one, and it sees this one, and oh yeah, no, that does work. I was about to say that does nothing, but it does do something, because there is a 1 here. So this square is a 3 or a 6, and that means there's only one square in row 6 that can contain a 1. And that's that one. Gives us, oops, 3, 6 pair now here. That gives us a 1, 7 here. We can, oh goodness me, sorry. Let's turn my mouse sensitivity down. That gives us a 6 there, which allows me to eliminate the 6 from this square. Now we've got a 1, 7 pair here. And if my earlier pencil marks are right, this square is now seriously restricted. Now I'm just going to check this, because I noticed there was a 7 here and I highlighted 1, 3 and 7 in the block, so it's possible whatever I was doing was complete nonsense. So what can this be now? It can't be a 1 because of the 1, 7 pair. It can't be a 2. Could be a 3. Can't be a 4, 5, 6, 7. Can it be an 8? Oh, it can be an 8. Oh, that's probably what I did. I probably pencil marked 7 when I meant to pencil mark 8. Can't be 9. Bother. How annoying. 6. But there is something interesting going on in terms of the 6s especially. If we look at these 6s, all interact with each other, and in fact there's only 2 places for a 6 in column 3, look. So if this is a 6, this is a 3, this is a 6, and that would become a 1. Not sure where that goes from there, but if this is not a 6, this has to be a 6, this is a 3. Right, okay, well that's interesting, because it eliminates the 3 from this square, because either this is a 6, in which case this is a 3, so there's no 3 here, or this is a 6, in which case this is a 3, so again there's no 3 here. So does that matter? So this square can't be 1, 2, 3 for the reasons mentioned, can be 4, can't be 5, can't be 6, can't be 7, 8, or 9. This square can only be a 4, which means this square is a 4, this square is a 2, look, we've got 2, 2 and this 2 here, this square is 2, this square is a 2, and what next? let's take a look at column 7 here. So I need 3, 5, 6 and 7. So this is a 3 or a 5. This is 3. Oh no, hang on. 3, 3, 5, 6 or 8. This is 3 or 5. This is 3, 6 or 8. 3, 6, 8, 5. Okay, all right. Okay, hang on. So this square can only be 3 or 5. So what I did there was I then tried to work back to see where that took me. So you can see, if for example this square is a 3, this square will be a 6, this square will be a 3, this square will be an 8. That's it. Okay, there we go. Right. So coming back to this square, if this square is an 8, this square is a 5. If this square is a 3, this is a 6, this is a 3, this is a 5. So either this square or this square is a 5. Therefore this square is not a 5. This square is a 9, which means this square is a 1. Now maybe that's the thing that we needed to do to crack the puzzle. 9, 1, no. I was thinking that would be better than that. I suppose we get 3, 5 pair in this block just to complete that row 7. So this is a 6, 8 now. I'm not normally, by the way, a big fan of chaining. It's just that this puzzle, there's a heck of a lot of interdependence between pairs of numbers. So that it just feels to me like, you know, this is a natural way to approach this puzzle. 1, 3, 7 or 9 to complete this. So this is 3, 7, 9. This is 3 or 7. This is 1 or 3. 1, 3 or 9. Oh, but hang on, we've got 3 and a 7 here, look, and now we've got the 9 here. Where can we place a 3 and a 7 in this block? Only in these two positions. And that means this isn't a 3. So this is 1, 5. This is 1 or 5. 1, 5, 8 here. So this must be a 6 or a 9 because we need to complete the row. So we've got 1, 5, 8, 3, 4, 7, 2, 6, 9, 6, 9. And can we crack it? 1, 6, 8 on. Oh, lordy. Oh, well, actually, if we look at this square, it seems to be very open. 1, 6, 8 or 9 are the options. But look, we have a 6, 9, a 6, 9 and a 6, 9 here. So if, looking at this square, I eliminate the possibilities of 1 and 8. If this was the situation, this is broken now, this puzzle, because whatever I pick into this square, let's say it's a 6, then the finished solution would show a 6 here, a 6 here, a 9 here, and a 9 here. But the problem with this is that there is no way that the internal logic of this puzzle distinguishes between that solution and a solution where this is a 9 in this position. Again, all that would happen is that these 4 digits would change polarity, if you like, and nothing else in the puzzle would change. Nothing other than these 4 cells changes, so there would be a uniqueness issue. Now I'm assuming this has been created by a computer by the looks of the screenshot we got from Matthias, and that'll mean that it's been tested and it should be a good Sudoku with only one solution. So that means this cannot be a 6 or a 9, this must be a 1 or an 8. And that, does it matter? Oh goodness. Maybe this square matters. What could this square be? 1, 2, can be 3, can't be 4, 5 or 6 or 7. or 8, or it can be 9. Bother. Oh. Oh. Ooh, yes, but this is okay. This is okay, I think. Let's have a look. In fact, I'm tempted to pencil. I don't think we need to pencil mark this in, but let me just do that in case that tidies it up, which it doesn't. I don't think. I think this can be anything, 1, 3, or 6. So let's look down column 9, and you can see that we have 3, 9, 5, 8, 3, 5, 6, 9. So not quite a quadruple. So we've got 4 squares there with 5 different unknowns. So the unknowns are 3, 5, 6, 8, and 9. But here we have a cell with just 2 possibilities in it that would complete a quintuple. So there is a bent quintuple going around here. Now, sometimes bent quintuples can matter. Let me just think about this one. Yeah, okay, it's yes. So if we look at this block, we can see I've fully pencil marked it. So there is either a 6 here or there's a 6 here. So let's think about those 2 options in the context of this quintuple. If this is a 6, this square here has to be a 9. And look what that does. 3 here, 5 here, 8 here. Remember this 8. So if this is the 6, this is an 8. Now if this is not the 6, we know the 6 will be here, therefore this square must be an 8. So we know we've got one of these binary states of existence again. Either there is an 8 here or an 8 here. So we must hunt in the grid for any cells that see both this square, and we can eliminate 8 from both of those squares. Now here it's absolutely massive because this square sees those 2 positions, so this can't have an 8 in it, and this square sees those 2 positions, so that one can't have an 8 in it either. So we get 2 digits resolved as a result of that. Now that might matter, I think. Now the one here gives us a 9, which means this is a 9 up here. Assuming my pencil marks are correct, this is a 6, 6, 9, like that. Now this square here is forced to be an 8. 3, 5, 6. I'm going slowly here because I don't want to make a mistake and ruin what ought to be a decent solve. 8, 5, 8, 1, 5, like that. This 1's now get resolved here, which backs us into the 7's at the bottom there, which resolves the 3, 7 at the top. The 1's and the 6's are resolved. Wow, this is just totally and utterly collapsed. 7, 1. Now if everything is correct, this should be a 6, which it looks like it will be, and this should be a 3, which looks correct. So there we go. Yes, Sudoku completed successfully. So thanks very much for watching a longer video. Some of the harder Sudokus are a bit time consuming owing to my slow brain and just the complexity of them. But I hope that was interesting for some of you. If you do enjoy the content, please do subscribe. We really appreciate it. And we'll be back soon with another edition of Cracking the Cryptic.